Information is brought to you by the Alco Controls Division of Emerson Electric. The skill of the professional is measured by the small things he does. Air conditioning and refrigeration systems give the service technician plenty of opportunity to demonstrate his skill with details. The typical air conditioning and refrigeration system is loaded with hundreds of little things that must all work together. Pressure set just right and balanced. Component sizes that are big enough but not too big. Settings that are in 1 or 2 pounds or degrees. Everything working to give the technician a system he knows will do a good job for his customer. The professional comes to know these details as second nature. Many of them are easy to know. A few are much harder. But understanding them makes for a much higher chance of installing the right system for the job. This program is about one of those details. The effect of head pressure and evaporator load on the superheat setting of an expansion valve. Setting a superheat is an important step in fine-tuning a system. A good superheat setting ensures that an evaporator is being fed just the right amount of refrigerant with little chance of liquid reaching the compressor. The accuracy of the superheat setting will directly affect how well the system will perform and for how long. In the conventional TEV, there are 3 things that set the flow rate through the valve: the setting of the valve, the bulb temperature, and the evaporator pressure that is read under the diaphragm. Evaporator pressure under the diaphragm will work against the bulb pressure above the diaphragm, moving the pin to open or close the valve. Adding to the evaporator pressure under the diaphragm is the superheat spring force, which is set by the technician. These 3 pressures will combine to set the pin position to feed just the right amount of liquid to the evaporator, until the 4th pressure in the valve, head pressure, gets too far from normal. Head pressure not only forces liquid through the valve seat, it also goes to work on the pin that controls the opening at the seat. Depending on the valve design, a higher pressure at the seat will either try to open the valve or try to close the valve. At the same time, head pressure is working on one side of the seat, evaporator pressure is at work on the opposite side. It is this differential pressure, or pressure drop, between high and low side that can shift the superheat setting of a valve by as much as 6 degrees or more. This situation occurs far more often than is generally known. The modern condensing unit is designed to be efficient and to use as little energy as necessary. To get this efficiency, the design uses bigger coils, more controls, all designed to allow system operation at low head pressures whenever ambient conditions will permit. Under a 100-degree condensing temperature, a typical medium temp 502 system will have a head pressure above 220 pounds per square inch. On the low side, the evaporator will be at a pressure of about 50 pounds per square inch. Taking into account the other pressure drops of the system, the pressure drop across the valve seat will be at about 150 psi. The amount of force this pressure will apply to the pin is directly related to the size of the pin. If it's a big valve and the pin is exactly 1 inch in cross-sectional area, the pressure difference will generate a force of 150 pounds. While valves of this size are rare, the pins in all conventional TEVs see some amount of this force. The bigger the valve, the greater the force. This same pressure applied to a smaller valve with a 1/4 of an inch cross-sectional area on its pin would still generate a force of 37.5 pounds. This force is at work as long as there is a pressure drop across the valve. If the service technician sets superheat with this head pressure in the system, his setting will remain accurate until head pressure drops. Now the 502 pressure on the high side will drop to about 160 psi. If the evaporator pressure does not change, the new differential pressure across the seat will be about 100 pounds per square inch. The new force across a pin of 1/4 inch cross section will be 25 pounds. There has been a drop of 12.5 pounds of force from the original 37.5 pounds that was on the pin when the valve was set. With a normal superheat spring pressure of about 12 pounds, it is obvious the setting originally made will shift. In our example, the drop in pin force will cause the valve to close off. This has the same effect as raising the superheat setting, except it gets done without the okay of the technician. The shift will be especially troublesome if the valve is trying to control at or near its superheat set point. Under these conditions, the three normal forces in the valve are near balance and the valve is barely open. The effect of a big shift in head pressure will be much greater under these conditions. It will be very easy for the valve to be forced to open under increasing head pressure or to close under pressure that is falling. A valve operating this way cannot accurately control superheat. We've seen that changes in head pressure can dramatically shift the superheat setting made on a conventional thermal expansion valve. Alco solved this problem over 25 years ago with its T series of balanced ported valves. The original balanced ported designs were for bigger valves with large ports. Alco has now released a new series, the HF series of balanced ported valves for smaller systems. The HF uses a pin design that is quite different from the conventional valve. Head pressure working on the pin surface at the seat cannot be avoided, but it can be counterbalanced. Head pressure will still apply its force to the pin, but it will also apply an equal and opposite force to a step at the diaphragm end of the pin. Whatever pressure the seat end of the pin sees, the other end also sees. The net effect is that there is no effect on the valve from swings in head pressure. The superheat setting the technician makes is the setting the valve keeps in high ambient temperatures and low. So far, we've confined our thinking to only one side of the pressure drop problem. We have assumed that most problems start with the changes that occur on the high side of the system. The extra force trying to move the pin has two components: high side pressure on one side of the pin and evaporator pressure on the other side. It is the difference between these two pressures that will try to move the pin. Since the swings in pressure on the high side are much greater than those on the low side, it is high side changes that concern us the most. But load changes can affect the superheat setting on a conventional valve. As load drops, so too will evaporator pressure. If high side pressure stays the same, the pressure drop across the pin and seat will go up and will try to open the valve. The evaporator will be overfed. Again, the balanced ported valve solves this problem by eliminating the effect of pressure drop on the pin. Regardless of changes in evaporator load, the superheat setting will remain accurate. Because the balanced ported valve is more responsive to load size, any one valve can cover a wider range of capacities. In the HF series, two models cover the range from 1/4 to 5 tons. The J and K models are fully interchangeable with currently available commercial refrigeration TEVs. They have replaceable power elements, and they may be either internally or externally equalized. A wide choice of temperature ranges are available, using any one of a list of available bulb charges. While the balanced ported thermal expansion valve has been designed for a system whose head pressure takes big swings, its accuracy makes it an ideal evaporator control for all systems. The HF Balanced Ported for accurate evaporator feed under all conditions.